Alright guys, so for today we're going to be going over 5.4, the fundamental theorem of calculus. Go ahead and please write down the definition, and when you're ready to go, hit play. Alright, by now I'm assuming that you've already written down the definition. Let's go ahead and talk about it. So first of all, in order for you to apply the fundamental theorem of calculus, you have to recognize that f has to be continuous in a closed interval. So we can take the antiderivative. And if that's true, then we can do a definite interval. A definite interval, remember, it's when you have an upper and a lower limit. So what you do is that this actually provides you with the area under the curve. If you're able to integrate and evaluate it between the lower and the upper limit, then you can find out the area between those two x values under the curve. That's really what the fundamental theorem of calculus says. Now today we're going to focus more on actually applying it rather than finding area, just so that you know how to use it. Okay? So I'm going to go ahead and do a couple of examples. And the first one I want to do is the following. We want to do the integral between 1 and 2 of x squared minus 3 dx. Okay? So I'm going to apply the rules that we learned last class. I'm going to undo the power rule here. So this is equal to, I'm going to add 1, so it's x to the third power. So that will be 1 divided by 3. 3 times that will get you an x squared, right? Minus 3x, and we're going to evaluate that. Here's how we do that. We're going to evaluate it from 1 to 2. Okay? Now, what you're going to do first is you're going to take your upper limit and you're going to plug that in for x. So what we're going to get is 1/3, 2 to the third power, minus 3 times 2. Once you figure out what that is, you are going to subtract and do the same thing but not plug in the lower limit. So 1/3, 1 to the third, minus 3 times 1. Okay? Now we take each one of this and simplify, we will then get our solution. 2 to the third power is 8, times 1/3 is 8/3, minus 6, minus, that's going to be 1/3, minus 3. Okay? Well, at this point, if we get common denominators here, so let's say this is going to be 8 over 3 minus 18 over 3 minus 1/3 minus 9 over 3. Negative 10 over 3 minus negative 8 over 3. Negative and negative make a positive, so negative 10 plus 8 is going to be negative 2/3, and that is going to be your solution. So let's summarize what happened here. We had to integrate the expression, and we have to evaluate it, and here's the notation that we use, from 1 to 2. Remember, plug in your upper limit first, figure out what that is, so in this case it was negative 10 over 3. Plug in your lower limit, figure out what that is, which in this case was negative 8 to the thirds, and you are always going to subtract them. Okay? Let's try one more, and then I'll give you one to try on your own. So let's do the integral between 1 and 4 of 3 root x dx. Okay, the first thing I am going to do is rewrite this problem as the integral from 1 to 4 of 3x to the positive 1/2 dx. Now we're ready to integrate. So we're going to add 1, so that becomes x to the 3/2, and divide the 3 by the 3/2. By doing such thing, I get, let's see, 2x to the 3/2. Now, one thing I forgot to mention in the last example, notice how these types of problems I'm not having to include a constant, and that's because I'm only focusing on a very specific part of the graph. In this case, I'm only focusing from 1 to 4. Okay? So that means I'm going to evaluate this from 1 to 4, which in this case is going to be 2 times 4 to the 3/2 power minus 2 times 1 to the 3/2 power. If I do that, 4 to the 3/2 power is the same thing as saying 4 to the first power times the square root of 4. So square root of 4 is 2, times 4 is 8, times 2 is 16. minus 2. That is going to give us 14. So that means that the integral of 3 root x dx from 1 to 4 will give us 14. For the next problem, I'd like for you to try it on your own, so please go ahead and pause the video, and when you're ready, hit play so that you can check your answer. So we have the integral from 0 to pi over 4 of secant square x dx. I'm assuming that you've already paused the video and tried the problem, so let's go ahead and go over it. The integration of secant square x dx is equal to tangent of x. So we are going to evaluate this from 0 to pi over 4. So hopefully you have not forgotten your unit circle. Tangent of pi over 4 minus tangent of 0. The tangent of pi over 4 is 1, and the tangent of 0 is 0. So 1 minus 0 is equal to 1. This problem's become very easy if and only if you remember your rules of integration and differentiation, for that matter. Okay, these problems can become very tough if you do not have your rules memorized. Moving on to our next topic, we are going to talk about something called the mean value theorem, which we've already covered in this class, but now we're going to talk about the mean value theorem when we're talking about integrals. So I'm going to go ahead and show you a diagram, and let's talk about it. The mean value theorem, before I actually explain this one, remember that the mean value theorem when we're doing differential meant that there was a point in between the closed interval where the average rate of change was equal to the instantaneous rate of change. Okay? Now, when we're talking about the mean value theorem, remember we've been focusing on finding the area under a curve. What this really means is I have a sketch right here where I have a function, so let's call this f of x, this right here. And I'm only interested between a and b, so I got a closed interval from a to b, and I'm interested about the area. So what this says is that once we're doing Riemann sums, you have two scenarios. You have scenarios where you have inscribed and circumscribed rectangles. What that meant, just to remember, is that remember how you had rectangles that were either above or below the curve, giving you an approximation that it was either an over approximation or an under approximation of what the actual area was. Well, what the mean value theorem for integral tells you is that between inscribed and circumscribed rectangles, there is one rectangle in particular whose area is precisely equal to the area under the curve. So in other words, we can use the whole concept of approximation to find the exact area under the rectangle. Okay? Now, on this diagram below, I've chosen this diagram so that you can truly understand. Notice how I have this rectangle. You know how to find the area of a rectangle is width times height in this case. Well, the area under the curve, notice that if I use this rectangle, I will be missing this red part right here, so I wouldn't be accounting for that. But I would be accounting for this part right here. Notice how these two parts are congruent, therefore this part would then fill in the void for here, and that would be the exact area under the curve, which happens to be the exact area under this rectangle, which is literally what the mean value theorem for integral states. So if we put that into words, here's what the mean value theorem for integrals say. If f of x is continuous on a closed interval from a to b, then there exists a number c in the closed interval from a to b such that the integral, the definite integral from a to b, is equal to f of c times b minus a. Let me explain to you what this means. F of c will refer to your height. So if we're talking about this rectangle right here, we call this c. Well, this right here would be f of c, which will in turn be the height of this rectangle. And we know that the area of a rectangle is, in this case, what I have here would be height times width. Now, do you understand that f of c is the height? Well, think about it. If b and a are these endpoints, that means that to find this entire length, you're going to take b minus a. And that's the reason why I have b minus a, and that gives you the width. Therefore, width times height gives you the area. And that is the reason why the integral would be equal to this in this case. So the area under the curve is equal to the height times the width. I'm going to repeat one more time what the mean value theorem for integral says. It literally says that there is one rectangle in which the area of that rectangle will be equal to precisely the area under the curve. Okay? So we're going to go ahead and try an example of what this looks like. We want to find the values of C guaranteed by the mean value theorem for integrals. So here's what we got. F of x equals to the square root of x between 4 and 9. Okay? So here's what we know. We know that to find the area under this curve, we would have to do an integral from 4 to 9 of the square root of x dx. Now, according to the mean value theorem for integrals, that has to be equal to one rectangle such that it's some height times the width. Now, remember, the width, it was b minus a. Well, isn't this a and this is b? So in that case, b minus a, that would be 9 minus 4. Well, the left-hand side, you should be able to apply your knowledge of calculus to integrate this. But I'm going to rewrite it just to make sure that you remember how to do this. So the integral from 4 to 9 of x to the 1/2 power dx is equal to 9 minus 4 is 5, so I'm going to say it's 5 f of c. So we're interested in finding this value out. Once we solve this, we're going to get a number for this, therefore allowing us to figure out what c is. Okay, so we integrate this, we're going to add 1, so that becomes x to the 3/2. So we're going to divide 1 by that, and I get 2/3. So 2/3 x to the 3/2. And we're going to evaluate that from 4 to 9, and that has to be equal to 5 times f of c. Okay, so if I evaluate that, 2/3 times 9 to the 3/2 minus 2/3 times 4 to the 3/2, that has to be equal to 5 times, f of c. Well, remember, taking a 9 to the 3/2 power is the same thing as saying 9 times the square root of 9. So the square root of 9 is 3. 3 times 9 is 27. And 27 times 2 is 54. So we got 54 over 3 minus, alright, so 4 times the square root of 4, so that's 8. 8 times 2, so that's 16 over 3. Is equal to 5 times f of c. Alright, so at this point then I have 54 minus 16, that's going to be 38 over 3 is equal to 5 f of c. Alright, so now I need to get rid of this 5, so I'm going to multiply by 1/5, so that becomes 38 over 15 is equal to f of c. Now notice that I am interested in figuring out what c is. So what I do know, I'm going to go back, I do remember that f of x is equal to the square root of x. Therefore, technically, what I know is that the square root of x is equal to 38 over 15. And what I want to figure out is what this x value is, and that will be the c value that I'm looking for. So in order to solve this, I'm going to square both sides. And I get that x is equal 38 over 15 squared. And I am done. It is at this value that the area of this rectangle will be precisely the same as the area under the curve. And that is the mean value theorem for integrals. Which takes us then to the last topic that I need to talk about with you. Well, actually, I'm sorry, it's not the last topic. The second and last topic that we need to talk about today. And it is called average value. The average value, really, all it is the value of f of c given by the mean value theorem for integrals. So hold on, wait a second. Let's just go ahead and review what this is one more time. So we know, according to the mean value theorem for integrals, that if we have an integral from a to b of f of x dx, that has to be equal to f of c times b minus a. Well, if what we care about is f of c, the value of f of c, then I can solve for f of c by dividing the entire thing by b minus a. If I do such thing, then I'm able to cancel out this b minus a, leaving me with f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. Now notice how I pull this out here. Remember, the properties of integral says that if you have a constant, you can pull it outside of the integral, and that's what I did. B minus a is technically going to be a constant because b and a would be the upper and lower limits of your integral, which are numbers, and therefore you can pull them out of the integral having 1 over b minus a. Okay? So literally, to find the average value, if you think about it, if you really think about it, you're going to just take the integral, the definite integral from a to b, and divide it by the difference between a and b. Okay? So let's try it. Let's find the average value. And use that word as a hint. It's the average, right? When you're finding an average in algebra, it's like you take the highest and the lowest number and subtract them and divide the total by that. So that's what we're doing. We're finding this definite integral and dividing by the difference between the highest and the lowest term. So here's what we have. F of x equals to 3x squared minus 2x from 1 to 4. So if I want to find the average value, the average value is equal to 1 over b minus a times the integral from a to b of f of x dx, which in our case is 1 over 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx. Well, that becomes 1/3, and this becomes, if I go ahead and integrate that, x to the third minus x squared between 1 and 4. Alright, so then I have 1/3, 4 to the third power minus 4 squared minus 1 to the third power minus 1 squared. Well, this is going to cancel away. Now I notice that I have 1/3 here, and here they have in common a 4 squared, so I'm going to pull out a 4 squared, leaving me with 4 minus 1. 4 minus 1 is 3. This 3 cancels out that 1/3, and 4 squared is equal to 16. Therefore, the average value for this function would be 16. Now, really what that means is that if I was to evaluate it at 16, that is the total area. That means that f of c is equal to 16. And I can figure out that c value by going back and using the mean value theorem. Okay? Last topic of the day then would be the second fundamental theorem of calculus. Fundamental theorem of calculus. I'm going to go ahead and abbreviate it. So the second fundamental theorem of calculus. If f is continuous on an open interval I containing a, then for every x in the interval the derivative in terms of x of the integral from a to x of f of t dt is equal to f of x prime. So make sure that you understand what this is saying. First of all, you're taking the derivative of an integral. So a derivative of an integral, there are operations that undo each other. So technically you would say, well, technically shouldn't this cancel out and then I should just be left with f of t? But notice how I'm not left with f of t, I'm left with f of x. Well, the reason for that being is that notice that this integral The upper limit isn't actually a constant. It's an actual function. So in order for you to do that, we can try to prove this out, but honestly, for the purposes of this class, you don't need to prove it. Here's what happens. If you integrate this, alright, and then you evaluate it at x and a, notice that x turns out to be a function. Now this is going to be a number that goes away. Now, when you plug in this number, you're going to get some constant. And after you take the derivative of a constant, it'll go away. That's the reason why this is not showing up here. However, when you take the derivative of the function, because you're plugging in a function into a function, then you're basically undoing the integration, and that's the reason why you have f. But instead of being in terms of t, which it originally was, you plugged in x for t, and that's the reason why you have the x there. Now, it is very important that you multiply by the derivative of the upper limit. Okay? So let's try that. Let's say that you have f of x equals the integral from pi over 2 to x to the third power of cosine t dt. And you want to find the derivative of that. Well, if you want to find the derivative of f of x is going to be f prime of x. Now, if you're going to find the derivative of the integral here is going to cancel out. Remember, all you got to do then is plug this value into here. So then this becomes cosine of x to the third, and multiply by the derivative of the upper limit, which in this case is 3x squared. If you go ahead and simplify things out a little bit, you get 3x squared times the cosine of x to the third, and that would be your final answer. If you were to try this and you were to take the integral of this, I promise you would get right back to here. Okay? I know this lesson was a little quick. I'll make sure that I cover any questions that you have on Thursday. Thank you for watching. The homework is already on the Learning Hub. I'll see you next week. I'm sorry, on Thursday, not next week.